Hey, 12th graders. We are continuing on with our geometric sequences and series. Last class, we talked about geometric sequences. So, of course, this class, we're going to talk about geometric series. The only difference between a sequence and a series is that instead of having commas in between, for instance, 1, comma 2, comma 4, comma 8, comma 16, comma 32, it becomes 1 plus 2 plus 4 plus 8 plus 16 plus 32. We're going to go into in this lesson about why we would care about adding all of these numbers up together in an application sort of way. But for now, that's really all you need to know is that the only difference between a sequence and a series is that a sequence is a list of numbers and a series is a sum of all of those numbers. We have a formula for finding the finite sum of a geometric sequence. In other words, finding the value for a geometric series. Finite meaning that we don't go to infinity, as we talked about in our last video. We go to only a specific number. We're only finding the sum of the first 10 terms, or we're only finding the sum of the first 4 terms, right? So that's the idea there. You have two formulas. Remember that it's written S sub n in your formula packet, but this is your sigma notation, right? If you see it as from I to n, we start at the first term, we go to the nth term, and U sub I means our first term, our second term, our third term, our fourth term, right? As I moves up towards that value n, we'll be finding all those terms. And then this sigma notation says, okay, once you have all of those terms, add them all up. Now, this isn't a formula. This is just a way to write things in a very fancy way in mathematics. The formula that you have in your formula packet is U sub 1 times r to the n minus 1 over r minus 1. Now, very important thing to know. This minus 1 is not in the exponent. That's a very common mistake that a lot of students make when they're using this formula. It's r to the n, and then whatever that value is, just minus 1. That's it. You'll also see in your formula packet that it's written in a different way. Oh, not equals, parentheses. Sometimes they also do 1 minus r to the n all over 1 minus r. There could be different reasons for using the different versions. The biggest reason that I can think of is that if r is bigger than 1, if your common ratio is 2 or 10, doing 10 minus 1 makes this positive, which is nice, versus if it was negative, it'd be 1 minus 10, and so it'd be negative 9 down here. So it would be kind of like a weird dealing with negatives situation. They're both the same formula. They've just been multiplied by -1, or sorry, multiplied top and bottom by -1. So they're the same formula, but you might want to use this formula if it's a decimal that's less than 1, but it really, truly does not matter. And I would actually just encourage you to use one or the other, but just so you're not confused when you see both of those formulas in the formula packet. So if I wanted to find S sub 6, which is the sum of the first 6 terms, I could use this formula. So U sub 1 is 1 in this case, and my r is, in order to go from term to term, I multiply by 2, so my common ratio is 2. So U sub 1 is 1 times my r to the nth power. Realize n is 6, which means I raise to the 6, and then just minus 1, and then I do this all over 2 my r minus 1. For these types of things, I think it's very important to have your formula and have your variables listed out in the prepare step of your problem. So then that way you can visually make that connection. R2, N 6, right? Maybe even say n equals 6 when you do S sub 6 to be able to say like, okay, cool. I know what number goes into what, and all I need to do is plug and chug. You can go ahead and figure this out on your own. You could also just add up those 6 terms, but it's 63, right? If you add up these 6 terms, it's 63. If you go through this formula, it's 63. This is the process that we use. Cool. So, of course, it's not always that straightforward. We're going to do example 5, which is still pretty straightforward. You'll see example 6 is the more applications use of this procedure. So it says find the sum to 8 terms, so the first 8 terms of the geometric series, and then it tells us, hey, it's geometric. We just need to go in and find out what are the pieces that we need. Well, the sum to the 8 terms, right? We're trying to chunk up a question that's being asked to us into smaller pieces, and in our prepare step, put those pieces down to say, okay, I need S sub 8. And if you have that already, if you're like, this is what I need to solve, and you're like, oh, I have a formula for that, go grab the formula in this moment. Don't even read the rest of it. Save it for later. Put some blinders on and just say, I'm just going to get this formula. Okay, it's up top. So I'm going to use u sub 1 times r to the n. And hopefully, I encourage you to notice I already have n. N is 8. So I might even just do r to the 8 minus 1 all over r minus 1. This formula helps us understand, right? We're just finding the sum of the 8 terms, S sub 8. We've put together a formula, put in what we know we need or what we can put in so far, and then just say, okay, I need u sub 1. Okay, that's pretty straightforward to spot. That's 7. And then r is just my common ratio, which if it's not easy to spot, remember you can just take any two terms that are next to each other and divide them out. Always take the second term divided by the first term, but we can see if we did 28 divided by 7 that is 4, but you could just use your calculator. Always stop and assess. If you got 1 over 4, if you got 0.25, then you did the wrong thing, right? You just need to flip that fraction around because we know intuitively, we know this should be getting bigger. So it should be a number that's bigger than 1. Okay, so now I can just plug in all the things that I need. I have S sub 8 equals u sub 1 is 7 times 4 to the 8th power minus 1 all over 4 minus 1. And that results in 152,915. And that's it. That's the process. Now, of course, the process gets complicated when we start to apply it. We have to make sure that when we're applying it, that we rely on this plan step, right? Being able to plan before we solve. The assess, right, comes at the end where we say, does this make sense? Yeah, it makes sense that it's a pretty big number because notice that by even the fourth term, we've got really solidly big numbers. And if I multiply that by 4, we're already getting to 1,000. So that makes sense that we're getting into the thousands, right? It wouldn't make sense if we got something like 100 because our fourth term is already over 100. So this is where the assess part really is handy. Of course, it makes sense because I'm your teacher. It should be right. But sometimes it's not right. And my having to stop and say, wait, does this make sense? Have I done all the right things? I still need to do that. Okay. Federico starts Bright Academy. The school fees are Japanese yen 2,500,000. The fees increase by 2% each year. Federico attends the school for a total of 6 years. And then, of course, IB problem, they're breaking it down into A, B, and C. 2% each year is a clue to you that when it's a growth by a percentage, this is a geometric sequence / series. And all it says right now is to write down the common ratio. And since we did this last lesson, I'm going to have you do this on your own. It says that it increases by 2% each year, right? So that means that it's going up by 2%, not that it becomes 2% each year, right? We talked about that last time, that if it says that it is this percentage, then that would be your common ratio. But if it's increasing by this much, then that means it's 100% plus 2%, which is 102%. It becomes 102% of what it was in the previous year, which means as a decimal, that's 1.02. Okay. The next problem then says to calculate the fees in year 6. So notice that the terms, like the wording here, can be tricky. You have to really pay attention. B and C could seem really familiar. And for B, you might be tempted to find the sum, S sub 6, right? But then you might get to C and notice, oh, calculate the total fees paid for the 6 years that he attended Bright Academy, right? And you might notice, oh, I'm answering the same question here. That's a good clue to you. I didn't read the problem accurately. I'm missing something. So the difference between this guy and this guy is this for a singular year that is the 6th year. A singular term is using your U sub n stuff, right? Versus a total of terms would be your S sub n. So this is the difference between which formulas we're using. We want to find U sub 6. And in my prepare step, I will write out the formula that goes with U sub 6. Okay, that's U sub 1 times R to the n minus 1. Oh, I already know what n is. It's 6. So if I do 6 minus 1, that would be 5, right? That's the process you kind of go through. And then you say, okay, what is u sub 1? Well, u sub 1 is, and then we can just take down that first term. And then I'm going to double check, what does my terminology mean? Well, in this case, it's the fee in year 1. Okay, good. U1 means year 1 here. So I am finding U6, right? If U1 was something that happened before the first year, then we would have to realize, okay, we're not actually finding U sub 6. Maybe we're finding U sub 7. So just always pausing to double check, what does your notation mean as you're going through with the notation? R equals 1.02. So we are finding u sub 6. Awesome. That's 2500000 times 1.02 to the 5th power. Okay, go ahead and calculate that and tell me what you got. If I wanted to the nearest yen, that would be 2,760,202 Japanese yen. Your notation in your calculator might have truncated it. It might have given it to you in scientific notation, or it might have just cut it off at some point. I think it might have just given it to you in scientific notation. Realize you can scroll up and press enter on that value if it wants it to the nearest yen, which this doesn't ask for the nearest yen, but I just want to talk about things that pop up in your tests sometimes. If it asks for the nearest whole number, you would have to have that 02 there. So if you scroll and press enter on your calculator, that value then will be brought down not in scientific notation. It'll be brought down as a whole number. So if you ever want to expand it to know, okay, I don't want this in scientific notation, I want to know what all those places are, that would be a way to do that. But 3 sig figs, you could have just had 2760000. That would have also been a correct way to answer it. Okay. So while this one wanted a term, just a singular term, this guy says, what are the total fees that Federico pays for the entire 6 years? What's all of the money that he has to pay for all of the 6 years? So it's the first year plus the second year plus the third year, fourth, fifth, and sixth. So that's a sum of all of those individual terms. Okay, cool. I have a formula for the sum. I'm going to write it out real quick. And I might realize, I already have an n. My n is 6, so I might go in there and replace that with 6. And I have my u sub 1. I'm going to rewrite it here just because it feels like it's an important part of the process to have it all nice at the top before we move down. And then I can go ahead and fill in. You can go ahead and type this whole thing into your calculator. And if you feel like you're having a hard time getting these values done correctly, just make sure that you're helping set yourself up for success, right? You can press Control Divide on your calculator and it automatically creates a division, like a fraction for you. So then you can just type it all in exactly as you see it, making sure you subtract 1 not in the exponent, but outside of the exponent. And again, it's given it to us in scientific notation. Maybe I don't want it in scientific notation, so maybe I do this guy, right? Scroll up and press enter, and it brings it all down. 15770,302. 15,770,302 Japanese yen. All right. So our first application, this would be a classic first paper 1 problem, maybe where they had it growing by a percentage and then they also had it growing by just a set number being increased every time to help you compare arithmetic sequences to geometric sequences, but just being able to separate out what formula to use when, pulling out those values as you need them to be able to then continue through with the process is important.